Welcome to a podcast looking at lots of examples of the derivatives of exponential and logarithmic functions. This is mostly centered on standard level, although there will be some references I'll make to the higher level as we go along. So keep that in mind. The derivative of e to the x from your formula booklet looks pretty straightforward. It's just itself. And the derivative of ln x is 1 over x. We'll take a closer look at each of those and then apply some chain rule, product rule, quotient rule examples. So this is strictly higher level. If we go back to what's called first principles, the derivative of e to the x would be the limit as h goes to 0 of f of x plus h minus f of x all divided by h. If you have a play with this, do some factoring here, factor out the common term of e to the x. This, of course, in this context would be a constant, so we can pull it through the symbol of the limit. And as you focus on just this limit as h gets small of this structure here, we can just kind of abbreviate how to approach this. If you did try to let h be 0, you would get 1 minus 1 upstairs here over 0, so you would get the so-called indeterminate form. However, if I just graph this, look at this as a function and graph it, it appears that as h goes to 0, which in this context would be x going to 0, which means you're approaching 0 from 0's right, or you're approaching 0 from 0's left. It looks like we're heading towards 1, and in fact we are. So at the HL level, this is a pretty decent justification for why the derivative of e to the x is just itself. So quick applications of this. If you were given y is equal to e to the 2x and you were asked to find dy dx, as it turns out, dy dx is going to be 2e to the 2x. A classic error is just to say, oh geez, well if e to the x has as its derivative e to the x, then e to the 2x should have as its derivative just e to the 2x. Well, that's too simplistic a view, because if you pull this apart and actually say, okay, the controlling feature of the problem is the 2x up in the exponent here, let's let u be equal to 2x. So right away we can get that du dx is 2, and then by virtue of choosing this to be u, then y is equal to e to the u. And then, of course, you can differentiate y with respect to u and simply get e to the u. And if you put these pieces together, because we're after dy dx, well, you chain once again through du. And so the dy du piece, which is just e to the u, times the du dx piece, which is 2, accounts for the fact that the chain rule kicks in. So that's not surprising. Let's look at a slightly more demanding version of it, and then I'll close with an algorithm that you might find useful. So if you're asked to find the derivative of this kind of structure here, well, you know that 1 over b to the n is just b to the negative n, so that maybe that's a healthier way to go about this. Although this problem can be attacked using a quotient rule, let's look at it in this context and apply a chain rule. So the controlling feature, once again, is this piece here. So let's let u equal that, and then du dx you can just see is negative 2x, because that's this piece here with a minus sign in front, because the derivative, of course, of that constant is 0. And then, of course, by default, once again, y is equal to e to the u, and classically dy du is just e to the u. And then, once again, we're after dy dx, so that's going to be the classic chain through this u bridge, as I like to call it, that you've created. So dy du is just e to the u, du dx looks like that, and you back substitute and you pick up that the final answer. You could more or less stop here or just bring the minus in front. It's not a requirement to take the e to the negative power and bring it back down into the denominator, but IB might say show that the derivative of this kind of structure here is looking like this. What's going on here? Well, there is an algorithm, so this will always work. If y is equal to e raised to any power, well, the derivative is going to be simply e to the power times the derivative of the power, or the so-called piece inside. That's classic chain rule. So here is the derivative down here being e raised to the power, because that was our f of x power, times the derivative of the power. That's classic chain rule. So this kind of algorithm will always work in this context if you like to memorize such things. Here is another related version where y is equal to this structure as you see here. The radical form is nowhere near as useful as its equivalent exponential form. So again, the controlling feature of this problem would be the piece literally inside here. So let's let u equal that, and then classically du dx, well, what is the derivative of e to any power? Building on what we just said, it would be e to the power times the derivative of the power, which is going to be just -1. So that's that classic chain rule. And then, of course, since u selected this piece in here to literally be equal to u, then we have that y is equal to u raised to the 1/2, and then dy du is equal to 1/2 u to the -1/2. And so then you've got that, again, what we're after, dy dx, you're going to chain through du. That's going to be dy du, that's right here, times du dx, which we picked up here. And so you back substitute, and once again you have something that looks like this. Or you could say, okay, this is, again, b to a negative power, bring him downstairs as 1 over b to that power, and then the 1/2 power sort of goes back to just being that root form. And so we picked up a negative sign that you see here in front, and e to the negative x stays upstairs, and the 2 is down bottom. So once again, IB could say, given y is equal to this, show that dy dx looks like this, and you have a little bit of extra work to do at the end to close that problem. Once again, an algorithm, what do you have here? You have a function, better seen here, a function raised to a power. So where y is equal to some function raised to a power, in much the same way that the derivative with that power rule was n times x to the n minus 1, well, here it's n times the function to the n minus 1, again, times the derivative of the piece inside. Classic chain rule, and that's exactly what you see down here. So the 1/2 that was right here swings down. There it is. Here's a repeat of the function, and then you do 1/2 minus 1, that's right here, times the derivative of the piece inside. So again, an algorithm can work on that one. Here is something that's a little bit more unusual to show that the derivative of this piece here actually has this kind of form. Well, your task would be to recognize that you have the product of two functions here. So I need first times derivative of second plus second times derivative of first. Start to do a little bit of work here to recognize maybe what's in common. Keep an eye on what you're trying to show. So all I've done here is sort of just combine terms to make it look a little bit easier to actually work with this. And what's going on here is that this x squared e to the 5x piece, well, that is just equivalent to y. So I'll let that be y because I need to get that into the system somehow. And then if I bring that over, I now have dy dx minus that is equal to this piece here. And this piece is pretty close to what it needs to be. If I can just multiply top and bottom there by x, I pick up that x downstairs. And so I get this piece here. And of course, this is the y value that it needs to be. So have a look at that. It is a kind of an interesting variation on this kind of setting. Mostly interested in application of the product rule.